Okay, hello. We're back for the clip number 19, okay? Uh, which at the end of clip number 18, okay, we have solved production planning under discrete time varying uncertain demand, okay, in which the main model, okay, is like we are showing here that uh, we only concern in the objective function with the variable cost, which means that it's linear cost related with the amount of production order and or the inventory minus, which means the number of back order, or the plus inventory, which is uh, the regular inventory. And today we're gonna start look into a more complicated cost function. And to do this, we have to go back to a classic paper by Wagner and Whitin way back in 1958. Okay, which is this is another classical paper in operation research called Dynamic Version of Economic Lot Size Model. Okay, written by Wagner and Whitin, published in Management Science Journal, year 5, volume 5, and the first issue. Okay, this is such a very important and highly influenced paper over the years until I think until today there's some research going on that have the origin on this paper. Okay, and we may look at the very first statement of the paper here. Okay, which is they say from the introduction part. Okay, so the first part is a abstract part. Okay, the first part we start with introduction part. The first statement is said by now the square root formulas. Okay, reference number 7, equation 8 below. Where is equation 8? Let's look at equation 8 below. Is right here. Yeah, this is the actually this is a formula that is well known in the subject of inventory management or inventory theory. We call economics order quantities. First derived it by we call a very famous engineer, okay, mechanical engineer, early in the 20th century, okay, between in the something like 1915, okay, year 1915. His name is Ford Wayne Harris, okay. He have derived that the amount of order quantities under steady state or constant demand, okay, and you need to find a lot size in order to minimize the total ordering and holding costs altogether. Yeah. And the resulting model is a formula that have a square root. Okay, this is such an iconic moment historically because way back this problem is some kind of managerial decision making problem because a factory manager would like to determine how much he should order or produce in this lot size in order to fulfill a constant rate of demand, and you try to minimize the trade-off between the setup and ordering costs and the holding costs. Okay. And the result come up with the we call the square root formula. In scientists, we it's very normal in science area that you're going to have some square root formula, but in management or economics application, you have the square root formula is quite something for them, I think, in that moment. So, but this formula actually they formulate the problem as a cost function that related to Q, and then they just use the first derivative, the necessary condition borrowing from calculus, okay, and then derive this formula coming out, and then they found the second derivative to uh, prove that whether this formula can minimize the original cost function. Okay, and that early 20th century, okay, in the year 1915. So it took maybe 40 years something, okay, before this paper coming out. And this paper just uh, adjust or modify the assumption of steady state demand rate to become a time varying demand rate. Okay, let's just say discrete time varying demand rate, which means that when you have instead of have a constant rate of demand, okay, you have a time varying amount of demand in each period in discrete time. Okay, and again you have a holding cost and inventory or inventory cost, and also the setup and ordering cost. Okay, and uh, the production cost per unit or the variable cost that appear in the previous model that we studied in the last clip is assumed to be constant in all periods. That this is a very different, very important assumption, because in our previous knowledge here, okay, the previous model that we study here, we assume that C sub I can be differentiated for each I, which means for each period, right, from 1 to n. So C sub I can be differentiated. But from the paper of Wagner and Whitin, they are constant. So once they are constant, you might look back at this formula, you see that summation Ci and the loss size of xi become a constant, because the summation of xi overall have to be fulfilled with the amount of total demand. Okay, but in case of uncertain demand, you don't really know what is the total demand is for all period altogether, because each period they have uncertain demand. But in this work of Wagner Whitin, since it's work on the deterministic time varying demand, okay, so you know exactly how much in the horizon of your planning that you want to produce or order, and it doesn't matter when and how much you produce. Overall, you want to produce to meet this amount of total demand. So, and if you have a constant cost, so it becomes constant. Okay, not the variable cost anymore. Okay, so the variable cost in this work will is only rely on the setup or ordering cost. Okay, which is a kind of fixed charge. Okay, per lot size setup. Okay, and the holding cost is the cost when in that period, if you can't uh, release your inventory to fulfill the order of your customer, okay, and you need to keep it at the whole period, so there will be some additional holding costs here. Okay, so we're gonna since this is a model that includes the uncertain situation, okay, we're gonna go to some of the classic work here, okay, that in terms of mathematical model, okay, it's appear in the paper that I co-wrote with Dr. Apisak, okay, that my former student, okay, and actually we have some part that refer to the old works, which is a Wagner production model. The is belong to the reference number 4 at the end of the paper, so we might take a look at that. Okay, so this is the fourth reference. Okay, this is here, which is actually the Wagner Whitin dynamic version of economic loss sign model, which is here. Okay, actually it's kind of strange that we refer to this paper, and when you look back at the paper here, okay, that I just showed you. Oh no, this is the Bowman, the dynamic loss sign. This is a paper that in the fourth appear in the fourth order, okay, on the reference part of that paper. And actually they didn't have any formula here that put it in here, but it's just an interpretation from this classical work, okay, to write that model out, okay. You will see soon, okay. But what I want to tell you, the real mathematical model that appears in the paper, original paper of Wagner and Whitin, is equation 1, 2, 3, 4, which is written in the form of what we call the functional equation, okay. When we talk about functional equation, we representing the minimal cost policy for period t to n, okay, given the incoming inventory I, which is the functional equation represent what we call the dynamic programming, okay. Okay. So when you develop dynamic programming methodology, you're gonna end up having some functional equation. So the approach that Wagner and Whitin propose here, okay, the result is they got some dynamic programming algorithm, okay, and what's important about this algorithm is that he have some developed some very important theorem. There are 4 theorems contained in this paper. Theorem 1, there exists an optimal program, which is optimal solution, okay, here, such that I of xt, okay, which is inventory is equal to 0 for all t, where I is inventory entering period t, okay. So it means that there exists an optimal program when you have a 0 inventory for all t, okay, which means that you might place just one lot size, okay, to covering all the remaining period, okay. So you just place order just once, okay, and use it for the whole horizon of planning, okay. And theorem 2 is that there exists an optimum program such that xt is equal to 0, which means that you didn't place any order, or summation I equal 1 to k of d sub j for set, which means that this one is a coverage of your order, okay, from period t to period k, okay. This is a very important theorem because it shows you that reduce a lot of possible alternative to place your order, because this one in for the simplification we get, you will always place your order when your inventory reach the 0 level, okay. You place this is a result from both theorem 1 and theorem 2. The optimal solution for this type of problem is that once you place an order, you place an order to cover the amount of demand for that period and a next couple of period up at as much as you want. But you will not place the order such that you need to place the new order when you still have the remaining inventory, okay. And so the theorem 3 here, okay, the x optimal program such that dt star satisfied by some x of t, this is look a little bit weird. You have to read from the start, and you can understand some. But I'm gonna wrap it up here, then come to theorem 4. Given 0 inventory at period t, it is optimum to consider period 1 to n minus 1 by themselves. This is when you reach 0 inventory, right? So that you can decompose the problem, okay, at period t, because you you can just optimize the remaining 1 to t minus 1 period by not, you don't have to worry about period t to period t plus 1 until period n here. And all these 4 theorems just imply just one indication to develop such an efficient algorithm, to dynamic programming algorithm here, is that the alternative or possible solution here is that you always place an order to coverage the amount of demand, okay, in each period until uh, uh, the inventory reach the zero level, and then you will place the next order. Okay, that's the nature of the optimum solution here. And but if you go back to the model that we studied before here, okay, which is this one, okay, that I showed you before here. If your C sub I is not constant here, okay, which means that your constant cost, your cost for each period is not constant. It caused the problem here because this idea of Wagner and Whitin is all the theorem that Wagner Whitin assume here. Oh, sorry, uh, will not work. Okay, what I say is that so this is only true. This four theorem only true when you only consider the setup cost. The setup cost in each period can be in each time varying period can be differentiated from each other. The holding cost can be differentiated from the holding cost need to make a constant. Okay, you have a constant holding cost. Okay, and the constant holding cost normally imply that you have a constant cost per unit for order of production. Okay, so when this assumption fulfill, okay, you can develop and use that functional equation here of dynamic programming to solve it. And in terms of algorithmic development, okay, it can be proven that this functional equation can be evaluated within on square. Okay, the complexity rely on the number of period, the square of the number of period. And over the year, there have been many research to reduce this complexity. Okay, it become to just like similar to what you found in fast Fourier transform. Fast discrete Fourier transform also have a complexity of O(n) square, right? Where n is the length of the data stream, and fast Fourier transform reduce it to O(n) log of n, log 2 of n. Okay, and this one also you can develop some more efficient algorithm to reduce the complexity. But the regular complexity itself is also polynomial time algorithm. So it's a class of the what we call the P of polynomial. There exists a polynomial time algorithm to solve this problem. But remember that it's because of this four theorem and based on the assumption that I just mentioned to you. Okay. So, and at the end of the paper, they just apply the algorithm to solve this numerical example. And then they get the results here. The optimal solution you get is the total cost of the is 864, and this is the ordering policy. Okay, you order for period 1 first, and then at period 2, okay, you order to cover period 2 and 3, 2 and 3, and then for the next order to cover for 4, 5, and then for period 8, one use option for policy 1 to 7, okay, imply. This is a kind of backtracking system, okay. We will try to solve using the current platform, and then we'll come back and compare solution here, okay. And then at the end, okay, they compare the results here with the classical EOQ and just show that the optimum cost, okay, from Wagner Whitin is always better than, because the EOQ or the Formula 8 is based on the constant rate of demand. So they can only use to approximate the problem, okay, and this result of the cost is that 931.80, which is more than 864 here. Okay, and that's the conclusion of the paper. So actually, based on this paper, okay, if you really consider what dynamic programming is working here, you can reformulate this problem based on this dynamic programming results as the shortest path problem for the network flow problem. Okay, but we're not gonna go to that direction. But I just mentioned it to you that based on this paper, you can continue to work on that, and over the year, people go to that direction and make several knowledge contribution in terms of more efficient algorithm and also more efficient of reformulation leading to a more efficient algorithm, okay, and so on, okay. But certainly they're facing some problem also. But you have to know that with all this direction here, this paper still did not consider what we are working on so far that we describe in this course, because so far we always consider some existing uncertain parameter in the model, which in this case for the production planning we consider the uncertain parameter for what we call for the amount of demand in this period. Okay, and we're gonna move on to look at the paper of Apisak and me. Okay, and actually this paper, you can see the title that is gonna bring us to what we study from the lecture 1 and some part in the lecture 2, that when you apply the Bender decomposition to solve, you from the title you might look at is this very similar to what we studied so far? The answer is yes, except that, okay, in this work we have to look at the basic formula from the classical Wagner-Whitin model here, okay, that under deterministic demand with time varying demand, which we refer to the variable d sub 1 until d sub t, capital T here, okay, this is the amount of demand, okay. So this is a very similar formula to what we study so far, except that the demand is constant, so there is no k index represent the uh, the pattern of or scenario of demand that can happen. There's only one scenario here. Okay, so the first equation is quite very similar and the same. But if you look at the paper of Dan6, they didn't have consider any I minus at all. There's no I minus, which means there's no back order. Okay, the paper of of Wagner and Whitin just consider only x sub t and I sub t here. Okay, so you can erase I minus here. Okay, and the cost function, okay, they also have here, and you have to know that c sub t is all the constant value equal for all t. Okay, so if there exists some constant values, so you can move constant value here, multiply by summation x of t for all t. Okay, summation t for of x of t, you know that it's very easy to know that you need to require the fulfillment have to be equal to summation of d sub t equal 1 to t, capital T, because demand is equal to supply here. Okay, and we don't have a summation GTI minus, we don't have a back order cost here, but we do have inventory cost here. So the first term can be ignored. Actually, the first term is constant. Okay, the second term is we didn't consider this possibility, but you can have a third term, which is the inventory cost. Okay, and you expect to have a constant inventory cost also, but it's not, this is not the what we call a constant just like the first term, because you don't really know what the inventory is going to be, because the inventory will always rely on your lot size. Okay, if you place a large amount of lot size, okay, you end up having a lot of inventory, okay, to keep then fulfilling the demand period after period. But you place a very low amount of order or setup, okay, the number of times that you place the order, okay, And that is the other cost that has been added in the model as compared to what we studied before, okay, in the previous clip, okay. We add this term is a summation t e sub t p sub t. This is the what we call the e sub t is what we call the setup cost, okay, at period t, okay, which is if you look at the paper of Wagner and Whitin here, okay, is the same cost as here. You look at the numerical example at the end here. Is this one is the same as S here, S sub t here, okay. This is the okay. The S sub t here is become E sub t in that paper. Okay, and next is when you look at this model, okay, this setup cost need to multiply by a new type of variable we call P sub t. And this P sub t can be either 0 or 1. Because of the nature of the setup cost here is that it doesn't matter how much you order, okay? But once you place an order, this is a fixed charge, okay? It's a constant charge, constant value that charges when you place an order. If you don't place any order, there's no cost. So the relationship of P sub t have to rely on the amount of X sub t, okay? And that leads you to an extra constraint, which is a constraint number 4 here, okay? This is a new one that has been added to consider this fixed charge and or setup cost to put in the cost function and the model, okay? Look at this equation for inequalities 4 here. Let m be a large positive number when m times p sub t have to be greater than or equal to x sub t. Why this inequality is logical and it makes sense to explain the nature of the setup cost. I can explain you to this, okay. You already know that e sub t need to be added to the cost function, or in other words, p sub t need to be equal to 1, okay, if e sub t for any t will be added into your cost value. P sub t have to be equal to 1, but P sub t have to be equal to 1 when x sub t is greater than 0. Okay, when x sub t is a non-negative value. Okay, P sub t have to be equal to 1. Let's look at the logic of this inequality. When m is a large positive number, you can assign m to make sure that m have to be greater than the largest value of x sub t that can happen, okay, for all t. And you can see that when x sub t is greater than 0, p sub t cannot be 0. P sub t can choose either 0 or 1. If x sub t is greater than 0, p sub t is 0, this constraint will not be satisfied, right? Because x sub t is already greater than 0, cannot be less than or equal to 0 when p sub t is equal to 0. So when x sub t is greater than 0, and p sub t can choose either 0 or 1, the only choice that will make this inequality to be feasible is when p sub t have to be equal to 1. Okay, so this also, when x sub t is greater than 0, p sub t have to be equal to 1. But when x sub t is 0, when you don't place any order at period t, p sub t can be either 0 or 1, can be both. But you say, no, when x sub t is 0, p sub t must be 0. But when p sub t can be picked either 0 or 1, look at the objective function c here. You want to minimize c, right? You want to make c as small as possible. When p sub t, you can select either be 0 or 1. You have a choice to select whether they can be 0 or 1. They will always choose 0, right? When e sub t is greater than or equal to 0. Which means that if for all period, you have non-negative or non-zero, okay, greater than 0 setup cost. just like the example that you saw in the Wagner Whitin paper, that in each period the setup cost always a positive value. Okay, so when E sub t is all positive and P sub t need to be select whether they're going to be 0 or 1, they have a choice. They always choose 0 because you want to minimize C. Okay, that's the logic of adding this constraint. Okay, and the resulting model here become what we call the mixed integer linear programming, because you have a nature of x sub t, I sub t plus, I sub t minus, still the default of the linear programming model greater than or equal to 0. But your x sub t here, okay, your p sub t here become the discrete variable with only two choices of either 0 or 1. Okay, it's an integer value restricted to be either 0 or 1. Okay, so there's two type of variable here, decision variable in the model. One type is a continuous variable, the other type is a discrete variable. So that resulting model we usually call the mixed integer linear program. Okay, and now you understand the model here. Okay, and we also talk about the paper here, and certainly they have a algorithm, the dynamic programming algorithm here, and they have a results of the application of the model here. Okay, but actually they didn't use anything about the model that we discussed in another paper. Okay, so what I'm doing here is that I'm going to solve this problem, the classic problem here in the paper of Wagner using this model. Okay, the model that we just discussed from the paper of Apisak here. Okay, this one. Okay, we're gonna put all the data used on this model. Certainly we will erase I minus, okay, and also the cost function of I minus and x of t. There'll be only setup cost and holding cost here, and certainly they have a time varying demand based on the problem. Okay, and I already uh, I already set up this model by on the Excel format here. Okay, certainly the I cost here and the setup cost over here. Okay, you might familiar with the number was taken from the data from the here of Wagner and Whitin here. Okay, this is exactly the same data here. Okay, this is setup, this is the demand and also the inventory cost. Okay, and we have here the here this is the demand. Okay, the same number, inventory cost per unit. Okay, the setup cost. Okay, and suddenly we have this is an x of t. Okay, x of t here, and this is the inventory I plus, and this is p sub t that restricted to be either 0 or 1. And actually you can see that this is already the same solution that in the paper of Wagner and Whitin was found. Actually it was solved already, but so this is a tree changing cell here. Okay, with the restriction that this set of changing cell or variable, you want to make it a binary variable, either 0 or 1. And the balance equation here, okay, certainly the left hand side number 1 is we implement this constraint, okay, from the paper of Apisak down here. Okay, we implement this one, constraints 2 and 3. Okay, you look at the model, constraint 2 and 3 here. Okay, is when you look at the Excel is this one, the left hand side number 1. Okay, the first one is for constraint 2. Okay, and the third one, okay, fourth until the last period. Oh, sorry. Okay, it's a mistake. Okay, this one. okay, until the last one is the third constraint, the third equation constraint, based on this one. You see the second one, when you don't have any I minus, it's only x1 minus I plus equal to d sub 1. And also for the remaining constant is I plus for t period t minus 1 plus x sub t minus I plus at t period t e plus b equal to d sub t. So we implement this too, okay, on the Excel here, in the left hand side number 1 here, or here. And you know that this has to be equal to demand, okay, the demand here, okay, according to this one, have to be equal to the demand. And we add the second type of left hand side here. This is based on this constraint, the fourth constraint, x sub t less than or equal to m times p sub t. Okay, this one, if you move x sub t to the same side, to the right hand side here, you get the inequality that m times p sub t minus x sub t have to be greater than or equal to 0. Okay, and this is what the inequality that we set up here. Okay, you can see that d2 is the m value, and you fix the address when you copy it to the other cell. Time g4 is the here. This is a 0 1 constraint, like p sub 1 here. Okay, minus e4 is x sub 1. Okay, and then we just keep using this for the next period, okay, but using the reference of m is equal to 10,000. This one minus x sub 2 and minus p sub 2, m times p sub 2 minus x sub 2. Okay, and all this, okay, it have to be greater than or equal to 0. Okay, that's to satisfy this m p sub t minus x sub t greater than or equal to 0. So once we already set up, this is the left hand side and the constraint, and all these need to be greater than or 0. So we're ready to run a software there. Let's look at the target cell also. The target cell become here, okay. Since you have inventory cost, setup cost down here, and your decision making is on only the inventory and setup cost here. So it's a sum product between both inventory and setup 0 1 constraint here, with the column of inventory cost per unit and setup cost, okay, per period, okay, within that period. Okay, so just a summation, sum product or dot vector between these two data range. Okay, you get here, and the solver model I already put here. Okay, if you can go back and trace it up, and there'll be three type of constraint. This, you want this cell to be minimized by changing the cell, is that all the order, inventory, and setup here is belong to the changing cell, and your first constraint is you want to make sure that all the changing cell related to setup we control is to be binary. Binary is a kind of setup that you want to make sure that I go back and I set up this, and then I chose this, and there was some bin here. Bin is mean that you can control this range of changing cell or decision variable to just make it either 0 or 1. And this is what we have done. Okay, and this is the constraint of it's run already. I'm sorry, I just put on the run. Actually, you're gonna get the same result. We don't have to wait here. Okay, actually they've already get the same result, but I to make it a little fun, I'm gonna reset it again. Okay, oh, I'm sorry, I didn't change it to Thai mode yet. I'm gonna say, okay, suppose this, oh, sorry, come on, man. Okay, 0. Okay, I'm gonna reset it, all the decision variable here. I'm gonna reset. Okay, so it's all will become 0. Okay, so this is the way to start. Okay, You want to minimize this, okay? Satisfying the constraint here, the left hand side have to be equal to the demand here, and left hand side too have to be greater than or equal to 0. And that's what appear in the solver model here. Okay, all setup, all variable related to setup have to be 0, 1. Okay, and the left hand side 1 equal to the right hand side, and the left hand side 2 greater than or equal to 0. And we chose the simplex LP. We can start solving it. Okay, take some time here as compared to if you use a more efficient machine here. Okay, it take a while here, but you can certainly solve it and start searching using some algorithm called the branch and bar. And you can see that you get, this is the same results. Okay, you get 864 here, and you place, how many times you place an order? 1, 2, 3, 4, 5, 6. 6 times. Okay, the first one you place an order to cover the first 2 periods. The second time you place order to cover 3 and 4. And then the third time you cover 5, 6, 7. Okay, and the fourth time cover 8 and 9. And then you just place order just for the 10 period alone. And then the last placement is here, is that you place an order to cover the last 2 periods. And the total inventory cost and holding cost and setup cost is 864. And if you go back to the paper of Wagner and Whitin here, okay, you would see that this is actually the same solution that the algorithm found using dynamic programming here. Okay. But when they show the solution is a little bit backtracking. Okay. Okay, the first placement you order period 11 to cover 11 and 12. And the second one you order at period 10, just 10 alone. Okay. The third one you order at period 8 and to cover 8 and 9. Yeah, since 10 or 11 you already 10, 11, 12 you already make a decision. So this one you place order at 8, so you need 8 cover with 9. And the next one you place an order from period 5, so it's going to be 5, 6, 7. And the fifth order is you at period 3, so you need 3 and 4. Yes, we got 5, you make decision down here. And so the remaining part is you place the order at period 1, which will have to cover 1 and 2. Okay, this process in dynamic programming we call, sometimes we call backtracking after you finish, because actually he just says a forward algorithm. Okay, if you understand dynamic programming, there's 2 technical terms they call the forward and backward. Okay, when you use the forward algorithm, you start make decision from the first period, okay, and finish at the last period. But to get the solution, you need to backtracking, okay, from the last period back to the first period. Okay, that's why they in this the interpretation or results look like this. It's not the same as what we found in over here in the Excel. You get the order and you can interpret it directly here, okay, from period 1. Okay, so this one just to go back and review the classical paper of Wagner and Whitin, but we didn't use the dynamic programming methodology proposed in the paper. Instead, we using the direct model here. Okay, refer to the paper for our pizza. Okay, appear here. Okay, by cutting off all the term that not include in the original Wagner-Whitin model. But as you know that to end this session, all of this we only consider the difference from the previous lecture is that we add a new fixed charge, okay, or setup cost here, okay, E sub t and P sub t, which we didn't consider this before. Resulting, you have a 0, 1 additional integer constraint here, okay, that make a problem a little bit more difficult, okay. And also we still haven't considered the nature of uncertain time varying demand, just like what we did in the when we only consider the variable cost here. Okay, so in the next part, okay, we will try to apply this, okay, the methodology that we learned from the previous script and use it to solve the problem that we the classical Wagner-Whitin problem with the next time we will bring the effect of the uncertain demand, okay, resulting to many scenario of the demand type, okay, and certainly we're going to start by attacking the problem using the Excel platform to show an example first. Okay, so see you in the next script. Okay.